Hello everyone, my name is Omar Farooq. I am going to share my midterm presentation. Okay, midterm 1. The first question is draw Fermi-Dirac distribution function in intrinsic silicon or where energy band gap is 1.1 electron volt at 300 K and 400 K temperature. The first question answer is here Fermi-Dirac distribution curve. Here we can see two curves. One is black and one is red. The black is on for 300K and the red one is for 400K. And from here we can clearly see that the red one is more sharp than black one because of temperature. And here one thing we can mention here that the uh, the Fermi level is at 0.55 electron volt. And the second portion of this question is calculate the probability function at 0.01 electron volt above and below Fermi level at 300 and 400 K. The answer is here. Yeah, we know at 300 K, KT equal to 0.0259 electron volt, or where at 400K, KT equal 0.0345 electron volt. And we know Fermi Dirac probability F equal to 1 divided by 1 plus e to the power e minus ef bhag kt. Here for above Fermi level, the ef e minus ef equal 0.0 on or plus, but for below e minus ef equal minus 0.0 on electron volt. So by calculating all this, here we can get at 300K and above Fermi level, the probability is 0.4, and above 0.0 on electron volt from Fermi level, and at 400K, the answer is here 0.43. Consequently, uh, at 300K and below Fermi level 0.6, at 400K and below Fermi level 0.57. Now the second question. Fermi level is at 0.2 electron volt below conduction band. Draw Fermi Dirac distribution function in at 300 and 400K temperature. Here red and black is for only reference. The answer is here. The blue and the pink on. The blue on is for 300K and the pink is on for 400K temperature. And here from here we can see the Fermi level is at 0.2 electron band, 0.2 electron volt. Yeah, the next question is Fermi level is 0.2 electron volt above valence band. Draw Fermi distribution function in silicon at 300 and 400K. Here also we added the reference black and red on, and blue and pink is for this question answer. Okay, the blue on is for 300K and the pink one is for 400K, and blue one is less sharper than pink one because of temperature, right? And our next question is explain what is the difference between the Fermi-Dirac distribution pattern at 300 and 400K temperature. We know more temperature, more electrons are excited and goes up to the valence band. And so from the above graph, it is clear that Fermi-Dirac curve is for 400K is sharper than 300K, and more electron occupied for 400K than 300K in conduction band. And from calculation we know 300K temperature KT equal to 0.0259 electron volt, and for 400K KT equal to 0.345 electron volt. And the next question is now midterm 2. The first question is a math, and here we have to calculate Fermi level as well as whole concentration, that is P naught. And here given that and the electron donor impurity equal 10 to the power 16 and 10 to the power 18, and temperature is 300K and 400K. For calculation, approximate ND equal to N naught, that is donor impurity equal um, electron concentration, right? So at 300K, Ni equal to, we know, 1.5 into 10 to the power 10. So we only explain that one, and similarly all these are happen, right? We know N naught into P naught equal to Ni square. From this equation, if we put the value of Ni and N naught and T, then we get whole concentration equal 2.25 into 10 to the power 4 per cubic centimeter. Okay, and for 400K, Ni equal to 4.56 into 10 to the power 12. If we calculate, then we get this value, and if we put this all value in this equation, then we get whole concentration P naught equal to 2.08 into 10 to the power 9 per cubic centimeter. Similarly, we calculate this 2 1, and at 300K temperature we find Fermi level, right? So if we take the reference as a intrinsic Fermi level, then the Fermi level is 0.347 for 10 to the power 16 donor impurity concentration, and for 10 to the power 18 donor impurity concentration, the Fermi level is 0.467 electron volt. And if we take the conduction band as a reference level, then Fermi position is at 0.203 electron volt for 10 to the power 16 donor impurity concentration, and 0.083 electron volt for 10 to the power 18 donor impurity concentration. Okay, at 400K temperature, uh, uh, when we take the intrinsic Fermi level as a reference level, that time the Fermi level is at 0.256 electron volt for Nd equal to 10 to the power 16, and for Nd equal to 10 to the power 18, the Fermi level is at 0.424 electron volt. And Fermi level here, if we take the conduction band as a reference level, that time the Fermi level is at 0.285 electron volt for Nd equal to 10 to the power 16, and 0.126 electron volt for 10 to the power 18 donor concentration. Our next, the last portion of question on answer is here. Here the Fermi-Dirac distribution function at 300K and 400K temperature, where Nd equal to 10 to the power 16 and 10 to the power 18. Here for 300K temperature, and this 2 for 400K temperature. And our now midterm 3 overview of this lecture. We have learned a lot of things in order to calculate the current density. Actually, our final goal is to understand how to calculate the current density for semiconductor, and controlling the current in semiconductor is our primary goal. Therefore, this lecture, this teaches us a variety of lessons, each of which is discussed below shortly. Firstly, we understand what is semiconductor. Conductivity between conductor and non-conductor or insulator. These types of material are known as semiconductor, right? And the more appropriate definition is here: the substance that can be controlled by changing the electron and hole concentration. That all types of um, materials are known as semiconductor, right? And um, energy band gap, the second is energy band gap. When two similar atoms are brought close to one another, their outermost orbit overlap and interact, and the energy band gap is created, right? The third one is Fermi level in semiconductor. We know we have valence band and we have conduction band, and Fermi level is located between this valence band and conduction band. Our This is the most important things we learn from this lecture is Fermi-Dirac distribution function and its importance, right? The working formula of Fermi-Dirac distribution gives us a way to find out the probability of occupancy of electron or hole in any energy level of metal at temperature. So Fermi-Dirac's distribution function is very important for us. The best equation to extract the current density uh, is the Fermi-Dirac distribution, and this equation is Fe equal to 1 divided by 1 plus e to the power e minus ef by kt, where k equal to Boltzmann constant and T equal to temperature, right? Current density of a semiconductor depends on the carrier concentration, that is actually we add some impurities and this concentration. Again, carrier concentration depends on Fermi-Dirac distribution function. That's why this function is very important to understanding the semiconductor. And our next, now electron and hole concentration. The total electron concentration is the integral over the interconduction band, and the total number of holes in valence band is known as hole concentration, and these two electron and hole concentration are calculated by these two equations. Now p-n junction diode. When p-type and n-type semiconductor are meet together, then a p-n junction is created, right? Donor level donate electron and becomes more positive state, and also leaving behind a positively charged p-ion that is here. An acceptor level receive uh, electron from valence band and becomes negative state and also become a negatively charged ion, and this is for here. And this junction is known as special charge region or depletion region. Both depletion region have higher resistance than a neutral region. Most of the voltage take place in special charge region or diffusion region, right? And the next, Fermi level position. Where the Fermi level is located for hot condition. Here we explain this one. For intrinsic, number of electron in conduction band and number of hole in valence band is exactly same. For this reason, Fermi level position is at the center of the energy band gap. And for p-type semiconductor, number of electron in conduction band is less than the number of holes. That's why the Fermi level is near the valence band. And for n-type semiconductor, number of electron in conduction band is greater than the number of holes in valence band. That's why the Fermi level position is near the conduction band. The next is degenerated semiconductor. Actually, what is degenerated semiconductor? It is extremely highly doped semiconductor, and it is used in place of metal in indicated circuit, right? Now, relationship between Fermi level, carrier concentration, and temperature. On temperature increase, there should be an increased probability of finding an electron in conduction band. This corresponds to the Fermi level rising up toward the conduction band, right? So if we increase the temperature and the Fermi level goes up, and if we decrease the temperature, the Fermi level goes down, and uh, it also changes its position by carrier concentration only also. Now compensated semiconductor. Actually, the process of adding opposite type of impurity to an already doped semiconductor is called compensation, right? N dopant are diffused into P dopant, P substrate to make N type. Similarly, P dopant are diffused into N type substrate to make P type. If a donor impurity is equal to acceptor impurity, then intrinsic semiconductor is created. And when Nd greater than Na, then n-type semiconductor. Then when Na is greater than Nd, then p-type semiconductor, uh, right? And all these phenomena are explained in this figure, right? The next is, this is the last topics for midterm 3. Drip current and diffusion current. What is drip current? Movement of charge carrier due to the applied electric field is known as drip current, right? With drip current, Fermi level is tilted. Here we can see Fermi level is tilted like this. Okay, without current, EF would remain horizontal. If there is no electric field, then this line should be this line should be horizontal, right? Energy band gap is tilted to plus voltage since electron moves down the tilted EG, and holes move up to the tilted EG, and the drip current is calculated by this equation. Now the diffusion current. The diffusion current, which is due to the transport of charge occurring because of non-uniform concentration of charged particle in a semiconductor. Actually, non-uniform concentration means here you can see high concentration of electron, here low concentration of electron. So naturally electron goes from high concentration to low concentration, that is diffused. Electron diffuse from high to low concentration, and that's why the name is diffusion current. And the diffusion current is calculated by this equation. This is electron diffusion current, this whole diffusion current. And we come to our final. Okay, thanks for watching and being patient. Thank you. See you guys.